Hello everyone, I'm Kuromeru. Today, I will introduce some matrix representations of Lie groups that are easy to work with. This will give you some material you can use to experiment on your own. Let's get started. A Lie group is something that has both the structure of a manifold and a group. You can imagine it as a matrix whose entries are represented by parameters. The transformations we saw in the previous videos are also examples of Lie groups. Though, this image applies only to the class of Lie groups that have matrix representations. The first one we'll look at is called the general linear group of degree 2. It can be written using real numbers x, y, z, and w, like this, excluding the case where the determinant is 0. In other words, these are matrices that have no zero eigenvalues. If the determinant is 1, it is called the special linear group of degree 2. For example, it can be written like this, such that x times w minus y times z equals 1. Furthermore, a subgroup of the special linear group consisting of 2 by 2 matrices whose lower left entry is 0 is called the Borel Sub Group. This is a very easy class to work with, because it is not only simple but also incorporates non-commutativity, while still being expressible with just 2 parameters. It can be written using a non-zero real number, x, and a real number, y. Like this. Heisenberg Group. This takes the following form. It is characterized by real numbers x, y, and z. This also has a certain simplicity, so it is easy to consider things like checking concrete examples. SON is called the rotation group or the special orthogonal group. It acts on n-dimensional vectors and represents rotations in spaces, such as the 2-dimensional plane or the 3-dimensional space. SO2 can be expressed, for example, using a real number theta like this. As for SO3, it can be represented, for instance, using 3 real parameters phi, theta, and psi. These have determinant 1, and they satisfy the property G times G transpose equals G transpose times G equals E, where E is the identity matrix. SO3 has many interesting applications, but when you try to do various calculations with it, they tend to become complicated. The orthogonal group, which is a broader class of Lie groups than the special orthogonal group, where the restriction of being special is removed. Let us denote it by G. Just like in SON, it satisfies the property G times G transpose equals G transpose times G equals E. However, the determinant is not restricted to 1. Even though the determinant is not restricted, it can only take the values 1 or minus 1. This is because 1 equals determinant of E, which equals determinant of G times G transpose, which equals determinant of G squared. So, determinant G can be minus 1, which makes this group strictly larger. This can be said to allow reflections. SON is a normal subgroup of ON. In other words, if you take an arbitrary element from ON with determinant minus 1 and multiply it with all elements of SON, you can generate all elements of ON. For example, in O2, let A be like this and G be like this. Then, the set A, G is equal to the set G, A, where G is SO2. The set G and the set A, G are the two cosets of O2 modulo SO2. Here, G and A, G are open sets. Using the cyclic group of order 2, Z2, we can write O2 modulo SO2 is isomorphic to Z2. Similarly, all elements of O3 can also be expressed in this way. A Lie group is said to be connected if it cannot be divided into two or more non-empty open sets. As we saw in the case of O(n), it can be divided into the open sets G and A(G). So it is said to be not connected. For the Lie groups that follow, I'll just give a brief overview for now, and plan to discuss the details on another occasion. SUN is a group that is deeply connected to spin in physics and to particle theory. In particular, SU2 represents the rotation of spin 1/2 particles. SUN is the group of matrices G that satisfy G times G dagger equals G dagger times G equals E, where dagger means the conjugate transpose. In addition, determinant of G equals 1. Especially for SU2, it can be represented using two complex numbers alpha and beta, whose squared magnitudes sum to 1. That is, absolute value of alpha squared plus absolute value of beta squared equals 1. SUN is also considered an interesting object in gauge theory. When the letter S is attached, as in SUN or SON, it indicates that the group is special, meaning the determinant of its elements is equal to 1. That means the unitary group UN can be seen as a version of SUN without the restriction determinant equals 1. At this point, the determinant of a matrix in UN is a complex number with absolute value 1. From the viewpoint of physics, unitary groups appear in various contexts: the full phase of spin wave functions, unitary gates in quantum information, and in ordinary electromagnetism, which is described by a U1 gauge field in gauge theory. The special unitary group SUN is a normal subgroup of UN. Just like in the case of ON, by using an element A in UN that is not in SUN, we can construct a coset decomposition. Let's see how any element of UN can be built from SUN and such an element, A. Take any G in UN, such that determinant of G equals e to the I theta. Now multiply it from the left by A inverse, then determinant of A inverse G equals 1. Which means this product is an element H of SUN. Therefore, for any element G in UN, there exists an element H in SUN such that G equals AH. This result is expressed as UN modulo SUN is isomorphic to U1. This time, we've looked at concrete examples of Lie groups. I hope this helps deepen your understanding. That's all for today. If you enjoyed this video, please subscribe to the channel and give it a like. Your support motivates me to keep creating more content. Thank you for watching.